Hi students, in this lesson we will continue our study of probability. We will be discussing independent and dependent events as well as conditional probability. So let's go ahead and get started. Events A and B are independent events if the probability of event B occurring is the same whether or not event A occurs. When we have independent events, the probability of A occurring and B occurring is equal to the probability of A times the probability of B. Let's take a look at some examples. For number 1, what is the probability of rolling a 1 or 2 on a 6-sided die and then picking a queen from a deck of 52 cards? We can indicate the probability using this notation here, the probability of 1 or 2 on a die and then a queen from a deck of cards. These two events are independent because the outcome of one event does not affect the outcome of the other. So this is equal to the probability of a 1 or 2 on a die times the probability of selecting a queen from a deck of cards. The probability of rolling a 1 or 2 on the die is 2 divided by 6 or 2/6 because there are 2 favorable outcomes out of a total of 6, and then times the probability of selecting a queen from a deck of cards because there are 4 queens in the deck of 52 cards. The probability of selecting a queen is 4 divided by 52, or 4 50-seconds. Let's go ahead and find this product on the TA84. We have 2 divided by 6 times 4 divided by 52. Enter. Math, enter, enter, will give us the simplified fraction of 1/39. Remember, probability can be expressed as a simplified fraction, decimal, or percent. Let's go ahead and give all three. And let's give the decimal to 3 decimal places, which will give us our percent to 1 decimal place. And we already have the decimal here. Because we have a 6 in the 4th decimal place, we round up to 0.026, which is equal to 2.6%. And again, these two events are independent because the outcome of one event does not affect the outcome of the other. For number 2, what is the probability of rolling a 6 on a die and then rolling an even? So the outcome of the first roll does not affect the outcome of the second roll, so once again these two events are independent. And therefore the probability of rolling a 6 and then an even is equal to the probability of rolling a 6 times the probability of rolling an even. The probability of rolling a 6 is 1 divided by 6, or 1/6, times the probability of rolling an even. The even numbers on a die are 2, 4, and 6. There are 3 favorable outcomes out of a total of 6, giving us a probability of 3/6. Let's go ahead and multiply here by hand. There's 1 3 and 3 and 2 3s and 6, which gives us the probability of 1/12 as a simplified fraction. As a decimal, to 3 decimal places, we have 0.083, which is equal to 8.3%. And now let's talk about conditional probability. The probability that event B occurs given event A has happened is represented using this notation here, which is read as the probability of B given A, or the probability of B given A has occurred. So for number 3, Amanda rolls a 6-sided die. On her first roll, she gets a 4, and then she rolls again. For part A, what is the probability that the second roll is also a 4, which we indicate as the probability of rolling a 4 given the first roll was a 4. Each roll of a die is independent, again meaning the outcome of the first roll does not affect the outcome of the second roll, and therefore the probability of rolling a 4 on the second roll given the first roll is a 4 is just the same as the probability of rolling a 4, which is 1/6. And let's just leave it as a simplified fraction. For letter B, what is the probability that the second roll is an odd, again given the first roll was a 4? And once again, given the first roll is a 4 does not affect the outcome or probability of rolling an odd on the second roll. The odd numbers from 1 through 6 are 1, 3, and 5. There are 3 favorable outcomes out of a total of 6, giving us a probability of 3/6, which simplifies to 1/2. They won't all be this straightforward. Let's take a look at some additional examples. And this table shows a set of scores by gender. So for A, we want the probability a student scored an A given the student was female. So because we're given the student was female, we're only concerned about this row here. Notice how there are a total of 41 females, 14 of which received A's. And therefore the probability of receiving an A given the student was a female is 14 out of 41, or 14 divided by 41, or 14/41. And let's go ahead and express this as a decimal as well as a percentage. 14 divided by 41 to 3 decimal places is 0.341. We round down because there's a 4 in the 4th decimal place, which is 34.1%. For part B, we want the probability the student is female given the student received an A. So for part B, we're only concerned about the A column, this column here. Notice how there are a total of 17 A students. Of the 17 A students, 14 are female, and therefore the probability the student is female given the student received an A is 14 divided by 17, or 14/17, which is approximately 0.824. Notice here we round up because of the 5 in the 4th decimal place. It is equal to 82.4%. For number 5, a home pregnancy test was given to women, then pregnancy was verified through blood tests. The following table shows the home pregnancy test results. So first we want to find the probability the woman was positive given she was pregnant. So because we are given she is pregnant, we're only concerned about this row here. Notice how there are a total of 85 pregnant women, 79 of which tested positive. And therefore the probability of positive given pregnant is equal to 79 divided by 85, or 79/85. And we are told to round to 4 decimal places. So now we'll convert this to a decimal. 79 divided by 85 to 4 decimal places is 0.9294. Next, we want the probability of being pregnant given a positive test result. So we are given a positive test result, and therefore we're only concerned about this column. Notice how there are a total of 84 positive test results. Of the 84, 79 are pregnant. And therefore the probability of being pregnant given a positive test result is 79 divided by 84. Converting to a decimal to 4 decimal places, we have 0.9405. Next, we want the probability of a negative test result given the woman was pregnant. So because we are given the woman was pregnant, again, we're only concerned about this row. Of the 85 pregnant women, notice 6 had a negative test result, and therefore the probability of negative given pregnant is 6 divided by 85. Which is approximately 0.0706. And for the last example, we want the probability of not pregnant given a negative test result. So we are given a negative test result, and therefore we're only concerned about this column. Notice there are a total of 72 negative test results, 66 of which were not pregnant. And therefore the probability of not pregnant given a negative test result is 66 divided by 72, which is approximately 0.9167. For number 6, below is a list of all the possible outcomes in the experiment of rolling 2 die. So the first number is the first roll, the second number is the second roll. We first want to find the probability the sum is odd. Remember, odd numbers are numbers like 1, 3, 5, 7, 9, 11, and so on. It should make sense half the sums will be odd and half will be even. But let's go ahead and highlight the odd sums. We have a sum of 3, 5, 7, 3, 5, 7, 5, 7, 9, and so on. Notice how there's a pattern in the odd sums. And half of these sums are odd, which means there are 18 favorable outcomes out of a total of 36. 18 divided by 36 as a simplified fraction simplifies to 1/2. We enter 1/2. Next, we want the probability of the sum is 5. Let's go ahead and highlight the sums of 5. And again, we will notice a pattern in the table. So we have 4 plus 1 is 5, 3 plus 2, 2 plus 3, 1 plus 4. There are no other sums of 5. There are 4 favorable outcomes out of a total of 36 outcomes, giving us a probability of 1/9. Next, we want the probability of the sum is 7. So we have 6 plus 1, 5 plus 2, 4 plus 3, 3 plus 4, 2 plus 5, and 1 plus 6. There are no other sums of 7. There are 6 favorable outcomes out of a total of 36, giving us a probability of 6/36, which simplifies to 1/6. The next probability is the probability the sum is 7 and at least one of the die is 1. So here we have the sums of 7, but now we have and at least one of the die has to be 1, and therefore we must eliminate the 5 and 2, 4 and 3, 3 and 4, and 2 and 5. There are only 2 sums of 7 and at least one of the die is a 1. So there are 2 favorable outcomes out of a total of 36. 2/36 simplifies to 1/18. And for the last probability here, we have a sum is 7 or at least one of the die is 1. So because we have or, we can go ahead and highlight all the sums of 7, but we also have to highlight all the rows where at least one of the die is a 1, which includes 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 1, 3, 1, 4, 1, and 5, 1. All these outcomes have a sum of 7 or at least one of the die is a 1. So we have a total of 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 favorable outcomes out of a total of 36, which gives us a probability of 15/36, which does simplify because 15 and 36 share a common factor of 3. The probability simplifies to 5/12. And now let's talk about and probability for dependent events. Dependent events are events where the outcome of one event does affect the outcome of the other. So if events A and B are dependent, meaning not independent, then the probability of A and B is equal to the probability of A times the probability of B given A has occurred. Let's take a look at some examples of this. For number 7, we want to compute the probability of drawing 2 clubs from a standard deck of cards, which is the same as drawing a club from a deck of cards, not replacing it, and drawing a club on the second card. We can indicate this probability as the probability of a club and a club. And the probability of drawing a club on the first card does affect the probability of drawing a club on the second card, which is why these two events are dependent or not independent. And therefore the probability of club and club is equal to the probability of a club on the first card times the probability of a club on the second card given the first card is a club. So let's take a look at our cards below. Let's highlight the clubs, which are these 13 cards here. So the probability of selecting a club on the first card is 13 divided by 52, or 13 50-seconds, because there are 13 clubs out of 52 cards, times the probability of a club given the first card is a club, let's just assume the first card was the 2 of clubs. Notice now, when we draw the second card, there's only 51 cards, 12 of which are clubs, and therefore the probability of selecting a club, given the first card is a club, is 12 divided by 51, or 12/51. And we're told to give the answer as a decimal to 4 decimal places, so now we'll go back to the calculator and find this product. 13 divided by 52 times 12 divided by 51, enter. Because we have a 2 in the 5th decimal place, we round down to 0.0588. For number 8, we want to find the probability of drawing 2 aces from a standard deck of 52 cards, which is the probability of drawing an ace on the first card and an ace on the second card. And the outcome of drawing an ace on the first card does affect the outcome of drawing an ace on the second card. These two events are dependent or not independent, which means the probability of an ace and an ace is equal to the probability of an ace times the probability of an ace on the second card given the first card is an ace. Let's go ahead and highlight the aces, which are here on the right. There are a total of 4 aces out of the 52 cards. The probability the first card is an ace is 4 divided by 52, or 4/52, times the probability of an ace given the first card is an ace. And again, let's assume the first card was the ace of diamonds. Notice now there are 51 cards, 3 of which are aces, and therefore the probability of an ace given the first card is an ace is 3 divided by 51. Going back to the calculator, because we have a 2 in the 5th decimal place, we round down to 0.0045. And now let's talk about OR probability. The probability of either A or B occurring is equal to the probability of A plus the probability of B minus the probability of A and B. Now sometimes the probability of A and B will be 0 because A and B cannot occur at the same time. When this happens, events A and B are mutually exclusive. If A and B can occur at the same time, then the probability of A and B will not be 0 and the events are not mutually exclusive. Let's take a look at 2 examples. Janelle draws 1 card from a standard deck of 52 cards. Determine the probability of drawing either a 10 or a 2. Because a card cannot be a 10 or a 2 at the same time, the probability of A and B is going to be 0 because the 2 events are mutually exclusive. Let's go ahead and apply the formula anyway. The probability of a card being a 10 or a 2 is equal to the probability of drawing a 10 card plus the probability of drawing a 2 card minus the probability of drawing a card that is a 10 and a 2. Looking at the cards below, we know there are 4 10s in the deck, and therefore the probability of drawing a 10 card is 4 divided by 52, plus the probability of drawing a 2 card is also 4 divided by 52, and then minus the probability of drawing a card that is a 10 and a 2. There are no cards in the deck that are a 10 and a 2 at the same time, which gives us minus 0. So, which gives us a final probability of 8 divided by 52, which simplifies to 2/13. And we are told to leave the probability as a simplified fraction. And for part B, we're asked to determine the probability of drawing either a 10 or a club. Now a card can be a 10 and a club at the same time, and therefore these 2 events are not mutually exclusive, and therefore the probability of A and B is not going to be 0. Let's go ahead and set this up. The probability of drawing a card that is a 10 or a club is equal to the probability of a 10 plus the probability of a club minus the probability of a card being a 10 and a club. So we know there are 4 10 cards out of 52 cards. Let's go ahead and highlight them. That would be these 4 cards here, which gives us 4 divided by 52, plus the probability of a club. There are 13 cards that are clubs. The probability of drawing a club is 13 divided by 52. But notice how in this case we counted the 10 of clubs twice. We counted it in the probability for a 10 card and the probability of a club, which is why we have to subtract the probability of a card being a 10 and a club. The probability of drawing a 10 of clubs is 1 divided by 52. So we have minus 1 divided by 52. So because we counted the 10 of clubs twice, this is why we subtract this probability once. This is equal to 1650 seconds, which simplifies to 4/13. Let's take a look at one more example of OR probability. This time we'll use the table where again we have test scores for males and females. If one student is selected at random, what is the probability the student is male or received a B? This is equal to the probability of selecting a male student plus the probability of selecting a B student minus the probability of selecting a student that is male and received a B. So looking at the table, the probability of selecting a male, looking at this row here, notice there are 22 males out of a total of 59 students. The probability of male is 22 divided by 59, and then we have plus the probability the student received a B. Well, here's the B column. Notice how there are 25 B students out of 59, so we have plus 25 divided by 59. And then we have minus the probability of a student being male and receiving a B, which are these 13 students here. We counted these 13 students in the male total as well as the B total, which is why we have to subtract this probability here. The probability of the student being male and receiving a B is 13 divided by 59. And 22 plus 25 minus 13 is equal to 34, giving us 34/59. For the last example, we want to find the probability the student received an A or is female. This is equal to the probability the student received an A plus the probability the student is female minus the probability the student received an A and is female. So the probability the student received an A, notice how there are 11 A students out of a total of 59, giving us 11 divided by 59, plus the probability the student is female. Well, the females are in this row here. There are 37 females out of 59, giving us plus 37/59, or 37 divided by 59, and then minus the probability the student received an A and is female. Well, the A females are here. There are 8 A students that are also female. The probability of A and female is 8 divided by 59. Again, we subtract this probability here because we counted these 8 students in the female total as well as the A total. We counted them twice, and therefore we subtract this probability here, which results in them only being counted once. 11 plus 37 minus 8 is 40, giving us 40/59. Okay, I hope you found this helpful.